In this video, we're looking at dimension in physics. This is the second series. We have taken the first series where we define dimension and the uses of dimension. But in this series, we need to recall that the base of our measurement is MLT. M is for mass, L is for length, and T is for time. When we have that, we have to find the dimension for pressure. Pressure is force over area. We know that force is mass times acceleration. But we know that the dimension for mass and force is mass times by LT minus 2. If we multiply this becomes MLT minus 2. We're going to carry this expression and we're going to put it here, MLT minus 2, and then we are dividing by L to the power of 2. Remember that we can have M0 and then T0, which is the proper dimension for area. Well, we know that 1 minus 0 is going to give me 1. We know that 1 minus 2 is going to give me minus 1. We know that minus 2 minus 0 is going to give me minus 2. So this is the dimension for pressure. So we're translating it here. M L minus 1, T minus 2. Now we are told to find the dimension for gravitational force. In this gravitational force, you need to know that F of G, which is force of gravity, is equals to G M1 M2, all divided by radius to the power of 2. If I should put 1 here and cross multiply, this one will come to this side, while this one will go to this side. We have that G M1 M2 is equals to F of G R to the power of 2. When we have done that, we know that G M1 M2 is equals to force. Force is mass times acceleration times by radius, and that radius will be represented in L from this base. And we're raising everything to the power of 2. Having done that, we can now have that G M1 M2 is equals to M times the acceleration is LT minus 2, and then times by L to the power of 2. We know that G M1 M2 will be equals to, this is now M, and then we have 1 plus 2, which is 3, L to the power of 3, and then we have T minus 2 from this expression. Then we can now divide by M squared, divide by M squared. Then G is equals to 1 minus 2, that is minus 1, M to the power of minus 1. Then this one will come down, then we have T minus 2. And this is the dimension for gravitational force. Let's put the expression there. Minus 1, let's call minus 1, L3, and then T minus 2. Well, if you want to see other way of solving this problem, we have a video where we solve only the question on gravitational force, and that is on UTME, one of the UTME question series. Now we're going to electromotive force. Under the electromotive force, we need to find the formula for electromotive force. And the formula for electromotive force is work done over charge. Electromotive force, which is EMF. EMF is equals to work done over charge. Well, you need to know that work done, or let's start with work done. Work done is force times distance. We know that force is MLT minus 2 times by distance, which is also measured in length. 1 plus 1, this is ML to the power of 2, T minus 2. Then let's find quantity of charge. We know that current is equals to quantity of charge over change in time. Change in quantity of charge over change in quantity of time. And then when we put 1 here cross multiply, this one will go to this side, this one will go to the side. So I have that change in charge is equals to IT. And if that is the case, I'm going to bring back my formula, EMF. EMF is equals to quantity of charge, work done over quantity of charge. And what is the work done? Work done is L to the power of 2, T minus 2 now, minus 2 now, all divided by IT. Now, if this one comes down, it becomes M, and this becomes L to the power of 2, and minus 2 minus 1. Minus 2 minus 1 is T minus 3, and then I have that I is equals to minus 1. So let's translate it here now. ml2, then we have that t minus 3, and we have that I is minus 1. Well, voltage is the same thing as work done over time. And if it's work done over time, it's still the same process of solving. So let's put it there. T by t raised to the power of minus 3 and current raised to the power of minus 1. Potential difference is the same thing as work done over charge. And if it's work done over charge, that means it's the same solving we're still going to have. So we have the same dimension. M raised to the power of 2, t raised to the power of minus 3, and then I raised to the power of minus 1. And then we have resistance. What's the dimension for resistance? We need to know the formula for resistance. And what's the formula for resistance? We need to go back to our knowledge of electricity. We know that voltage is equals to IR. And if voltage is equals to IR, we are dividing by I, divide by I. We know that R is equals to V over R. How to say that? I know that R will be equals to V. V is voltage, which is this guy that is up at the other side. So we're going to have ML to the power of 2 and T to the power of minus 3. And then we have I to the power of minus 1. And then we're going to divide that by I. Now I is here, so we're going to minus 1 minus 1. So that will give me L to the power of 2 and T to the power of minus 3 and then I to the power of minus 2. So that will become my resistance to L to the power of 2 and T to the power of minus 3 and then I to the power of minus 2. So the next thing is electric current. So how do we find the dimension for electric current? Well, electric current, which is I, is equals to a change in charge over a change in time. Well, if you look at this formula, you'll find out that in dimension, our aim is to represent the physical quantities in the base of mass, length, and time. Let's bring this dimension here. Do we have anything like mass in this formula? The answer is no. So mass is 0. Do we have anything like length in this formula? Anything like length? No. The answer is no. So length is 0. Do we have anything like t? Yeah. We have t here. And if t should come up, is t is equals to minus 1. And then we have q, we have just 1 q. So this is the dimension for electric current. We have M0, we have L0, we have t minus 1, and then we have q. Now finally we have the 1 for kinetic energy. What's the dimension for kinetic energy? We know that kinetic energy, Ke, is equals to 1/2 mass times velocity raised to the power of 2. This 1/2 is constant, but we know that m will represent the mass, and the velocity is Lt minus 1, and then everything raised to the power of 2. We know that these two will be distributed into the bracket. Now we know that this becomes ml raised to the power of L to the power of 2, and then t to the power of minus 2. So this is the dimension for kinetic energy. Alright, so this is all we've got for you in this video. This is the second series of dimension. In the subsequent series, we'll be going to more practical and more questions that is higher